Hello, Ben.
Hello, John. How are you doing?
Oh, man, I am, first of all, so excited my cats are getting along. And second, so excited for 2.5 new Rust releases.
2.5, you say? More like 2.1, actually, I'd say.
Ah, I see what you did there. That was very clever. Very clever. I'm pretty excited about these. I think both of these have like pretty serious improvements that I'm excited to get into.
There's some definite really big user-facing improvements in these two releases, but I think they're more quality of life things than real, like, significant, dramatic changes that shake the foundations of the language. But still, I think people are going to enjoy these.
I don't know. Stabilized inline assembly is probably yeah.
Well, we'll get to that. Oh, no, don't jump the gun like that. We got to have some amount of mystery.
I'm sorry. I take it back.
Come on. Okay. You listeners, please forget what you just heard, because that doesn't exist, because right now it's Rust 1.58. It is January 13th, 2022. Rust 58 just came out, and we're talking about captured identifiers in format strings.
This I believe is a topic that you know a decent amount, Ben, wouldn't you say?
I mean, I know a decent amount about that. I don't want to take credit for implementing this or like RFCing this, but I've been I've been involved in surrounding efforts for this, and I've probably talked about this. I think I've spoken about this in a few different podcasts. But in this case, so what's new in this release is that if you're familiar with format strings from other languages, like if you're if you're used to C, for example, you're used to the current like Rust style of you have like some kind of token somewhere in your format string, and then later on you have the name of the thing you want to sub in. So currently in Rust, you would say the example here is hello, opening brace, closing brace, and then after the string you have like some identifier like foo. And in other languages like Python, what you can do is, instead of having to have a list of things where first a string, then a comma, then like thing one you want to print, thing two you want to print, you can just put those things inside the string itself. And so it makes things read a bit more naturally. It can get out of hand if you're not careful. But so, for example, the new hello world, if you have like world assigned to a variable called foo, you can just write a string of hello, open brace, foo, closing brace. And so that way you can avoid having to have an extra list of things afterwards. And it's actually pretty nice. It's a nice little like quality of life thing. The thing is, though, that unlike, say, Python, in Python, for example, you can put arbitrary expressions into format strings. And so Rust isn't willing to go that far just yet. This is kind of just a taste of what could be. There's no guarantee that it will ever grow beyond this. So some people would like, for example, the ability to access struct fields here as well, because if you can access a variable, there's really no risk in also letting you just look at the field of a struct. It's still a constant time operation, just there's a thing in memory somewhere, give me the value, all done. More radical would be to let you access, say, methods on a thing. And so now you're running arbitrary code, which like might be happening just from like having a format string somewhere, which some folks might not like, might be too implicit. So we'll see. There's plenty of ways to possibly expand this feature that may or may not happen, and it's still like very up in the air. But for now, if you just have simple needs, that's a great thing. It's a great little quality of life thing for, especially for new users, because I mean, hello world examples like this are really prevalent in a lot of documentation. Also, like tests can use this. Also, not just println, any macro that uses the format machinery gets this for free. And so we have the panic macro gets this. We have the unreachable macro, which we'll talk about later, also gets this. So anything like that in Stud gets. Also, if you use any of your own crates, so the log macro provided by the log crate also gets this for free. And so it's actually a really nice little just magic upgrade that every macro can now take advantage of just by relying on the format args macro.
Yeah, it's really neat. I also only learned by reading the release notes that you can use this for parameters as well, right? Like if you're formatting like a floating point number and you want to specify the precision, like the number of decimal places you want to include, that can be a variable too, and gets the same kind of inline captured identifiers as you get for the actual variable itself.
Oh, that's cool. I didn't know you could actually capture that. That's neat.
Yeah, I mean, I only realized by reading it, which was, it's almost like this is the point of release notes. Yeah, I think this is a change that has been in the pipeline for so long, and I'm really excited to see it land now. I think this is a major ergonomic improvement.
I know that one of the other the thing I've probably talked about before is the future work that I've worked on, or possibly laid the groundwork for, is the ability to have actual format strings, like in Python. Right now, this format machinery works in quote unquote format strings, where format strings are kind of a DSL that only works inside of certain macros. So if you had actual format strings, like so today in Rust we have, say, byte strings. You stick a B on front of your string literal and you get a byte string, or like raw strings. Put an R on there, you get a raw string. You can imagine like an F in front of your string literal, and it could like give you this behavior by default, and then that could like desugar to a format args macro invocation, say, and then you could like also pass that to things. And imagining someday, I'm weird, so macros, right? Macros are cool, but like macros are great in the hands of users for letting users extend the language without having to like actually go through and like pester the devs and like get a thing upstreamed. It lets you extend the language in your own way in very small ways. But my opinion is that a widely used macro is kind of like a bug report against your language, right? Where it's like saying, hey, we have this thing that's like kind of a hack on the language, and so if I'm a user, I can't like control the language, so I can extend it. That's great, but you control the language. If like you have, this is your language, just make it so I don't need this. And so like the argument is like if we just had like say variadic arguments, right? So currently the reason that we like previously the reason that like println had to have this machinery was because it like takes apart the format string in compile time. But if that's all being delegated to an actual like secret compiler internal thing, now the only reason that println exists is let you pass in more than one argument to the macro. And if you just had format strings, you could have a println function that only ever took one argument that was just the format string itself. So you could have println no bang parenthesis f and then your string, and that would be like, I don't know, pretty cool. I don't hate macros, to be clear. I just think that there are some cases where we can think about more regular solutions to certain problems. So who knows?
Yeah, no, I think you're right, and I think it is a good way to think about language design too, right? Which is, why should your standard library get to be special? Um, like, why can't you extend these same capabilities to users of the language without having to essentially use escape hatches,
Mm-hmm.
basically reducing the number of escape hatches needed over time.
Moving on, reduced Windows command search path. You want to take this?
Yeah, so this is a fun one. This stemmed out of, I think, a CVE that was published for ripgrep, where um, some users realized that ripgrep executes commands as part of things like searching decompressed files. Like if you're trying to search, an XZ compressed file or something, ripgrep will decompress it using the XZ command and then search the output of that command. And on Windows, the way that the standard library executes commands is using this create process API, which is provided by Windows, but it searches for binaries in a slightly weird way in that it also includes the current directory. So this means that if, in this case, ripgrep was executing, XZ, then it would look for xc.exe in the current directory and execute that over, XC provided by the system, which is really unfortunate, right? It means that if you git clone some project from the internet and it happens to have like a malicious xc.exe in there and you run ripgrep, then ripgrep would end up executing that file for you, which is not really what anyone expected. Andrew, the maintainer of ripgrep, I think correctly identified that while this is a problem in ripgrep, it's really a problem in the standard library. Like, it shouldn't be the case that we allow on Windows execution of binaries from the current directory, because it really is a security risk. And so what changed in 158 was that the command type in the standard library, this is standard process command, now uses the same search path as on other platforms, which basically means it searches the path environment variable, it searches the systems directory and the Windows directory and stuff, but it does not look in the current directory. Which is the same way things work on Linux, for example, where if you want to run something from the current directory, you have to say, // and the name of the program.
Right. And I'm curious, is this some kind of like old recommendation from like Windows to do this kind of thing? Because Linux does not do this. And so I'm wondering why this deviation in behavior occurred.
It's interesting. I think this is more that this is just how Windows traditionally worked, right? They have this like create process function in the Win32 API, and this is just its behavior. Like if you open CMD on Windows and you're not running PowerShell, just regular CMD, and you run a command, I think it really just runs the command from the current directory if one matches the name of the command you're running, which is convenient. It's probably not the most safe default. But Windows cares a lot about backwards compatibility, like Linux does too, arguably. And because they had the API work this way, they couldn't really change it. Whereas I think in Rust here, we're sort of saying this is a bug and you shouldn't get platform specific behavior for command. You should get, the documented Rust behavior everywhere. There's another change from the standard library, and this is probably one that's gonna make the most people notice that something changed. And this is more additions of the must use attribute in the standard library. Do you want to talk about must use? I think we've mentioned it before.
Yeah, so if you've used Rust, you've noticed how if you call any kind of operation, say like an IO operation, that returns a result. And if you don't then actually look at the result, and so I use IO as a good example where sometimes you might want to just like write a thing, and then I don't care if it's succeeded or whatever. I'm like just making a kind of a shell script or some simple thing, a little test, and I might just say, foo.write some buffer. And then if you do that, and don't actually like ever inspect the result that gets returned, you'll get a warning. This is called the must use warning. It's kind of misleading. It's probably called should use, I guess, because it's not actually an error. It's only a warning. You can obviously promote them to errors if you want to, like any warning. But the idea is that there are certain types where to not use them might be masking some kind of bug. And so in this case, like because like these IO APIs don't require you to actually access the result to continue. So many APIs that return results like store it's because you want to get some kind of value back, and that value is stored inside the result in the OK arm. But like for an IO API where it's kind of like, just do it and then like tell me if there was an error, it's much easier to ignore it and just like forget to check it. And so you should be checking it and making sure that, either at least bubbling it up with the question mark operator.
Yeah, and this happens a lot in C libraries, especially where people just, don't check the return value because nothing screams at them if they don't.
Yeah, people make mistakes and kind of like, and I don't want to say lazy, but I mean, programmers are kind of lazy, but we gotta get our work done and not necessarily like focus on the small stuff, but like sometimes we should. And in this case, this must use attribute just says, hey, like you probably intended to look at the result of this thing. And so originally it was just for, I think, result, but it's been expanding more and more. And nowadays you can also use it on functions too, to say like, not just, I don't want every value of this type to warn, but like for this function, definitely, just no matter what it returns, just warn if they don't use this result. So I believe there's all kinds of things now tagged with this. Do you happen to know the list?
Ooh, that's a good question. Let me see if I can dig that up. I wanted to also point out that there's sort of a heuristic that they've developed as part of the RFC for Rust for must use, which tries to get at when is it appropriate to use. And I think it's something like anywhere where the return value is the primary effect of the function. So the idea being that if you have a function that doesn't really do anything except produce its return value, then if you don't check the return value, then why were you even calling the function?
Mm-hmm.
I found the PR now, and it's actually a tracking issue that tracks 25 pull requests, and I think there's about 800 additions. And as one way to see how large this is one of the PRs is add must use to remaining STD functions A through N.
And they say Rust has a small standard library.
Yeah, I know, right? Well, I think the realization here was that there are a lot of functions where not checking the return value probably means you're doing something wrong. Like I know that I've run into problems with this in the past with stuff like checked add and checked sub, because they don't mutate the number that you're calling them on, they return the modified, added, or subtracted number. So just calling them doesn't actually do anything. Your original number is left the way it was, and that can be really confusing. And this is definitely an error that's hit me in the past.
Yeah, and from like a language design perspective, there's kind of a there back like in the early days of Rust, this was more of a big topic. But the idea of what is a linear type versus like an affine type, the idea of a linear type is a type that must be used. Where like use is kind of a vague, nebulous concept, but the idea is that if you have a language with a linear type system, then you can guarantee that the user uses something. This is kind of like a halfway hack towards a linear type system, and I guess you would classify Rust as an affine type system where things are required to be used 0 or 1 time. That's the whole ownership thing, is you can own a thing, but you can also just like not use it. You could just like never use this thing. So it's an interesting consideration that we're moving more towards a sort of like faux linear type paradigm over time.
Yeah, it's true. Yeah, I'm reading through the list here, and like so many, I think basically all of these are, yes, clearly you need to use the return value here. It's stuff like character to digit. It's stuff like basically any method that's called like as underscore or is underscore, because the return value is what you care about. Um, but less obvious ones are things like arc downgrade and weak upgrade, right? So these are things that turn an arc into a week and a week into an arc for reference counting, where it's not immediately obvious when you call this, you're not modifying the thing that you have, you're creating a return value that you need to deal with. Um, there's things like for path with extension, which returns a path with the extension added. It does not it does not change the current path to have that extension. So it's all sorts of things like that where they're really just, if you weren't already using it, your code is probably wrong. I think that brings us to stabilized APIs. So for stabilized APIs, there's nothing too major here. File options is kind of nice. So the file type, standard FS file, gained an options sort of helper static method that constructs an open options type for you. So open options has been stable for a while, and it's basically a way to set a bunch of options for a file you want to open. Like for example, you could say, I want to open it in append mode or read only mode, or read and append but not write, or I want it to be truncated if it already exists. All that you can are sort of more advanced ways you can customize how a file is opened. And traditionally, you had to like use standard FS open options and create a new one of those and then like call .open on it. But now that there's a helper function on file, you can just do, standard FS file : options and then .append true, .read true, .open, and then get that back. So you don't really need to know about this additional type. It just makes things a little bit more concise, which is nice.
I wanted to highlight some of these unwrap unchecked, which are on option and result. And you'll be familiar with unwrap if you use Rust, where it's you have an option and result, and you're pretty sure. Either you're pretty sure you don't care whether or not you have a none or an error case, and you just want to get the thing out. Just give me the thing. So these are unchecked variants, which are analogous. So for indexing in Rust, if you use the indexing syntax on a vec or on a slice, it will panic by default if you index out of bounds. And if you don't want that panic, if you're pretty sure, or you don't care, I guess, if you index out of bounds, there are get unchecked variants, which just let you get the thing. If they're unsafe, obviously, so they're unsafe functions, and they just like there are no checks. You just like you gotta know what you're doing, and you can get them. And so these unwrap unchecked methods exist to do the same, but for options and results. And I think these are interesting, actually, not because I think you should use them. I think you probably shouldn't use these. I think you should probably, in almost all cases, just use unwrap and not use unwrap unchecked, because unless you're profiling and you realize that like any of these checks are actually causing any kind of slowdown, it really isn't worth it to introduce unsafe code into your code base. Just for the sake of using these functions and like I don't know, saving a single like nanosecond of of checking.
Yeah, the benchmarks would really have to show that it's the panic code that never gets executed that's causing slowdown or instruction bloat or something that matters in
Yeah.
like a super hot loop.
But despite that, I think these were good additions, even though I don't think you should use them. And the reason is that standard libraries, we can kind of like look to, for example, like NPM with JavaScript, where JavaScript has kind of like historically, I don't know about these days, it's much bigger these days, but historically, JavaScript standard library was quite small, and it led to kind of a proliferation of lots of like nano libraries, like with like a single function, a single convenience thing in them. Also, in Rust specifically, it really matters where your unsafe code comes from, like what like underlies your thing. So currently out there are crates that give you unwrap unchecked. People obviously want this kind of thing once in a while, and so rather than have people one rely on a crate that gives you like a single method on option or result, and two contains unsafe code, it is one of the best features of, or the best, the what I think one of the prerogatives of the stud is to encapsulate unsafe patterns, so that kind of like you can kind of be sure that they're kosher, they're legit, and two, to kind of like prevent this proliferation of like micro libraries, because obviously having cargo is great, having a big dependency tree still is kind of a pain, just in terms of like the current watchword of the day is supply chain attacks, with like how do you know the person who like has control over your dependencies actually isn't sticking key logging you or running a crypto miner on your system, that kind of thing, although you wouldn't be able to tell with the Rust compiler running at the same time, right?
Yeah, exactly.
Yeah, even though I don't think you should use these, I think this is an interesting case study in like why it makes sense to add things that maybe you should be careful of using to stud, because it's just it should be, it's like, I don't know, if it was like a manifesto for stud, it would be like, okay, unsafe code patterns, encapsulate these, like have all these here. Ideally, you shouldn't have any unsafe code of your own in your own libraries, your own crates. I say ideally, obviously there are exceptions.
Yeah, and I think we've touched on this in the past too, that one thing Rust really tries to do is to have a standard library that's sort of not very broad, but very deep, very complete in the things that it does support. And I think this is more of that, right? Where like we want to make sure that the standard library has all of the, functions, methods, helpers that you would want for option. You should never need another crate to give you things on option, because we fully support option and sort of take responsibility for all of the ergonomics of option. I don't think I had anything super interesting from the detailed release notes under Rust or Cargo for 158. So I think we can move on to the point release that happened for 158. So this one was due to a CV, and in this CV, we're not going to go into like a lot of detail. There's a pretty good explanation in the security advisory that we'll link to in the show notes. But basically, this is a vulnerability that isn't really Rust specific. Like it is an issue in the Rust standard library, but it is one where I think attackers, or I think it was a group of security researchers actually, that discovered that the standard libraries of a lot of different languages, including I think C and C++, have this vulnerability. And it's basically a race condition in recursive removal functions from the file system. So specifically for Rust, it's in standard fs remove dir all, where remove dir all promises in its documentation that it does not follow symbolic links. So like soft links, where one file or one directory is really just a pointer to a directory that lives somewhere else. Remove dir all is supposed to not follow that link and instead just remove the link itself, and then not recurse into such link directories. And there's a race condition in the implementation where there's a check for whether something is a symlink. And then separately, there is the recursion into that directory. And it turned out that that code was written in such a way that an attacker could have something be a normal directory and then like remove it and replace it with a symlink just after the check for whether it was a symlink, but just before the standard library code recurses into that path. And so this is something where the Linux kernel, for example, actually provides a way to mitigate this attack, but the standard library wasn't using it, in part because I think that mitigation is somewhat new. And that also means that there are operating systems like macOS before version 10.10 where this can't be mitigated because the operating system doesn't provide a way to not have this race happen. The security advisory has more details on this. It's a pretty interesting issue. It's something that shouldn't really affect a lot of users because it requires that an attacker has the ability to like add symlinks and remove directories and add directories in a place where your program is like in the working directory basically or in the a directory where your program is operating and calling removed or all. But if you are in that situation, this is definitely one to watch out for.
I mean, you say there's no way to mitigate it, but what I would do is I would just have it erase everything by default and then check whether or not it was a symlink, right? So there you go.
Well, the problem is erasing requires that you recurse.
That was a joke, by the way.
Oh, damn it. Damn it. I'm bad at those joke things. Oh, wait. I know what to do. I did it. Did I do that right, Ben?
I heard it.
Great.
It was there.
But yeah, I think this is a good lesson in like that there are a lot of latent bugs in not just in Rust but in standard libraries. Like the fact that this is a latent bug in like the C++ standard library sort of tells us that ultimately there will be new classes of attacks or even old classes but new ways to trigger them over time. And I'm really happy to see the Rust release team sort of having a good process for this and making it really clear in the announcements, like what the bug was, what the fix is, what the limitations of the fix was. I found their announcement for this and the security advisory really easy to read, and that's major props to them for that.
Now, you say you're happy, but I hear you did have to spend a lot of time on your own end fixing or working because of this bug.
Yeah, I mean it's like whenever there's a security release, right? Like anyone who consumes Rust at scale has to go deal with it, and that happens to end up being part of my job. But even so, like in that capacity too, I'm happy that the write up about what the problem was and the mitigation was so thorough because it made my job easier. I think that brings us to 159, and I'm very excited for 159 because it is getting very close to Rust 2.0, I hear.
What makes you say that?
Those are the rules, right?
When it gets to 99, you think it gets to 2.0?
Yeah. Is that not the case?
Well, I think that would
have
have
I
been
been
the case
tricked
for
all this time?
1.9. And so actually, by that logic, we're on Rust 15 by now. We're about to be to Rust 16.
That seems scary. I don't Rust
16.0.
Yeah, no, I'm not okay with 16.0. That sounds like something went wrong somewhere in the line.
Sounds
here.
like a browser release now.
Yeah, that's right. What is this, Chrome? So obviously the headline feature of 159 is inline assembly, which has been on the sort of menu listed as coming soon for probably years now. But it's landed and it is glorious, let me tell you. I think one of the things that's really nice about the assembly thing here is they didn't just go, we're just going to plop down the, inline assembly syntax that's used by, GCC or Clang or anything. We're actually going to think really thoroughly about the problem space and how we want to solve this in a rustic way. And I think they really succeeded there.
Yeah, so the history of this feature. So inline assembly, if you're not familiar with like system stuff, if you're like from Python or JavaScript, like this is a feature that's been like in C since forever, essentially. But I say in C. It's not actually in C or C++. It's in various compilers, right? So in like GCC or Clang, there are extensions that you can use to access inline assembly. And so in that case, it's kind of slightly more standardized in Rust now than it is in C. As far as, Rust isn't standardized at all. But someday, when it is, fingers crossed, you will have actual kind of like, if you write a compiler, here is the spec that you write it to. And so there is some amount of portability for inline assembly, which is actually pretty cool. And it's useful and important because even though it was unstable for so long, there are some things you just can't do without it. It's kind of like how like so in Rust. When it comes to unsafe code in Rust, I kind of like split them into two worlds. One is unsafe code because you're like want to go faster and you can it's not because you can't do a thing, it's just because you have like some performance need that you just can't do otherwise, right? So and you're using it, okay, that's fine, you need to go faster here, this is a hot loop, I understand. The other is to do things that you literally just can't do, and very often that means something like calling into C because you're calling some kind of like syscall on the platform directly, and there's just like no way of doing it. The platform library is written in C, so you better just like make an unsafe call and worry about that there.
Or even lower level, right? Like you need to issue like a specific CPU instruction because you're writing like bootloader code.
Yeah, and that's the exact use case that inline assembly is great at, where you just have like a single instruction, you just want to run it. This is just the CPU, like, hey, let's CPU, do this, and it can be like, gotcha. And so like no OS involved, nothing but the hardware right there. And so it's kind of a one of those things where like to be like put on your big boy pants and be a real language kind of to gatekeep there shortly. People have like in the past like looked at Rust and said, okay, you like, cool, here's your language, but like, where's your inline assembly? And so now we can be like, it's right here. Aha. It's stable now.
Yeah. And do you want to talk about why it has to be unsafe? Because this might not be immediately obvious.
I mean, so in the same way that C is unsafe, so Rust, safety in Rust is a big topic, and it's more about what you can't do than what you can do. Right. And so when you call out to C lets you do plenty of things, and Rust can't prove a lot of what C does is safe by Rust definition of safe. Right. And if it were so easy to define that in C, then why would anyone ever write Rust? We would just we would just figure out how to do this in C. The problem is that C lets you do too much. Right. It has too much power to do things that can't be proven. And there's this kind of like interesting like dichotomy here where like the more expressive your language is, the less that you can prove about that language. So like the idea is Rust lets you do less, but by doing less, it lets you know more about your program. And so because C lets you do too much and assembly lets you do way too much, and that's why it's unsafe. You can do all kinds of nasty things where Rust just isn't like Rust, the language doesn't know anything about like registers or like the stack or like, any of these things that inline assembly can theoretically change and tweak. And so it is kind of caveat emptor, where once you get in there, like make sure you know what you're doing, because like there are no more rails. It is all just like up to you to know what you're doing. And so like this is again one of those things where ideally you wouldn't need to ever write it, right? We were talking just about encapsulation of unsafe code in the standard library, where ideally, so for a long time now, like it's actually been fairly tractable for folks to not need an assembly for most of what they do, just because like Stood like provides things like say the black box function, which is actually unstable, but forget that for now. Like, so the idea is that
I guess intrinsics is maybe the example. Yeah.
also, yeah, intrinsics too. So various things that like are kind of like CPU ish, or like a single like instruction are kind of like there's a thing called intrinsics, which kind of like the compiler lowers these to LLVM things, which are themselves implemented with the appropriate assembly for various platforms. So by like doing this, it's kind of like alleviated the need for an assembly. But there are some things you just can't you can't possibly satisfy every use case this way. If you're doing something like writing an OS, if you are Linux, you can't possibly hope to ever upstream everything you need into the Rust standard library. You just sometimes need to write in that assembly because you just need to talk to the CPU. So this is a great day, I think, for us, because this is like been like there's been a macro for this since about 2013, well before Rust 1.0. But back in the day, it was pretty. Well, I'm not gonna say simple. It was definitely a lot of work even back then, but it was more or less just passing LLVM assembly directly, like what LLVM expects of an assembler. Which is it worked and it was functional. But if you ever want to have any backend that isn't LLVM, that's going to cause problems. And so this isn't necessarily about making your assembly portable. If you as a user write inline assembly, then there's a good chance that you have to care about your platform and maybe even what compiler you're using exactly. But it's more about, can any kind of Rust compiler ever re-implement the same semantics if you're tied that closely to LLVM? And so it's kind of a trade-off where, yes, many of the things that are currently happening in inline assembly in the stabilized version, which we have now, are kind of tied to what LLVM is doing, but it's much less than it used to be, where it's like many of the options and the features are now much more standard and like aren't just like, okay, here's what LVM does, do that for everyone forever.
Yeah. We should also point out that the assembly here is also not completely abstracted away, right? So the instructions that you have available, for example, are architecture dependent, right? Like it's not as though in stabilizing assembly we like stabilized all of the possible assembly instructions you could have and what they translate into for each architecture. Nothing like that. Like you still use the appropriate verbs in a sense for each architecture, and which ones you can use is going to depend on the architecture you're targeting. So it's still like fairly low level here. It's not like a completely new language was invented. That would be a major undertaking.
Yeah, I wanna shout out to Amanu D'Antras, who was kind of the mastermind of Inline Assembly, wrote the RFC, implemented a whole lot of this, along with like many of folks who contributed. But like kind of Amanu has been pushing it forward for several years now, and deprecating the old LVM ASM macro, and like it's just been a ton of work even to get this far. And this is just like the foundation. Where, so as you mentioned, it's not really its own language. It's kind of like it gives you a kind of like standard and reasonably stable interface to what any reasonable compiler should give you for assembly. But it's not like an actual DSL. You can imagine. So I think D, the language D, has like their own kind of like assembler, like a DSL that's like built into the language. But that's like a step beyond what we have here. The thing is, though, that because of that, they have much less platform support, because you have to do that for every single platform that you want to support. Yeah, you can imagine someone writing their own kind of like custom DSL, like their own crate, right? Where they provide a macro, where they provide a DSL, where that lets you kind of like, I don't know, write some special, unique, very nice variant of inline assembly that just compiles to this. So if you want a nicer assembly macro, you can make that now, and it'll be stable, and it'll continue to work. So that's a work for the library authors at this point.
Yeah, the other thing I want to shout out for this is that because this effort has been going on for so long, we've also gotten to the point where this is really well documented. I read through the Rust by example for inline assembly, and it's really, really good. Even if you're not super familiar with assembly yourself, read it. It's a fascinating read, and it talks a bunch about the syntax and why it is the way it is, and it's going to teach you a bit of assembly as you go as well.
Yeah, and documentation is also being improved as we speak. So currently, like, if you go to use this macro, it lives in stud stud arch ASM. And if you go to that location in the docs, it's kind of not as good as it could be, where it just links out to the aforementioned Rust by example pages and to the Rust reference. And so the former is how would a user use this, and the latter is like how would a user really use this. And so it's like very involved. And so they're kind of like an in-between sort of like API level documentation that's being written right now to put in stud at the stud arch ASM location. And so it's coming along. It's going to be even better in the future.
Yeah, I also want to mention one more subtlety around inline assembly, which is the difference between the ASM macro and the global ASM macro. This is a little subtle, but basically, the ASM macro generates assembly code sort of where it is. It's going to be integrated into the compiler generated assembly code of a function. And I think the compiler is even allowed to turn that assembly code into a separate function and generate calls to it rather than inlining it into the function. So the ASM macro is sort of a little bit constrained in how it gets to operate. The global ASM macro is literally like put these assembly machine code words here. So with global ASM, you could do things like put them in the top level of a file to generate a complete function definition. You can't do that with the ASM macro. So that's sort of the difference here, that global ASM is like a literally insert instructions here, whereas ASM is a little bit more principled in terms of how it interacts with the surrounding code.
Next up is destructuring assignments. And so this is actually kind of interesting. So if you're, I like to use Python as my example. So in Python, if you have, there are tuples in Python, just like in Rust. You have parenthesis, foo, comma, bar, parenthesis, and that's your tuple. And then you can swap them. It's a fun trick in Python to teach destructuring assignment, where if you have, you can put parenthesis bar comma foo equals parenthesis foo comma bar, and it'll just swap the contents of those two variables. It'll say put this in this and this and this, and it'll behind the scenes just like do it for you, and it's great and funny. Rust has a similar thing, actually more powerful in just pattern matching. So if you use pattern matching in Rust, like you can match on a tuple, and also one of the more intermediate things that you can do in Rust is that you understand that patterns work in more contexts than just match. You can use them in if let, but you can also use them in signatures for functions. If you want to, like, if you're taking a tuple, you don't need to like have a tuple foo and then on line one say let a b equals foo. You can just say parenthesis a comma b parenthesis and then the type of the tuple, and then inside the function you'll have a and b as just bound variables. Obviously, that works only on infallible quote unquote matching, where there's no possible chance to fail, because what would happen if you like passed in, say, like the wrong kind of thing for, say, an option, because you can match on options too, right? You can say some foo or none. So any kind of like an infallible just means like a match where there would only be one possible arm, or where a one arm would compile. But previously, destructuring only worked in let. So in the let assignment. So when you were originally declaring the variables. So what this new change is it lets you use destructuring in normal assignment contexts too. So if you have let mute A and let mute B, you in the past couldn't say unpack the so imagine the API standard IO, like, so what's the channel API?
MPSC channel.
Yeah, the MPSC channel, where it gives you both a port and a channel.
It's like a transmitter and a receiver, or a sender and a receiver.
It gives you a sender and a receiver. And so as a tuple, and so it's very common to, like, whenever you get this, you can say, like, let sender comma receiver equals the result of this tuple. And so now you could have a pre-declared let sender receiver, and then later on say in its tuple of sender receiver equals the result of this macro. Or you could even have mutable binding, so you could say, like, let mute sender equals something, let mute receiver equals some other thing, and then later on you could just mutate it as normal and then overwrite. So you could even have, like, if you just wanted to bind only one of them. I'm not sure why. Not in this is a bad example for binding only one of them, but you can imagine a different context where you might want to only bind one output for a pre-existing variable, and that works now. So, like, you would just say parenthesis foo comma underscore. Underscore is the usual thing in a pattern to ignore drop a thing, and then you would just bind one thing. And so it's just a way of making Rust a bit more regular as far as users are concerned. It's actually kind of tricky under the hood to implement, because it's not really feasible to implement the full space of pattern contexts. Here, just like randomly on the left-hand side of an assignment, kind of it complicates the grammar just like far too much to really consider, because there's a lot of different things that you can support in patterns. So what this does, it just supports the most common things in patterns, which just so happens to be most of what you'd want this feature for. So it works out pretty well. So its tuples are supported, slice patterns. So with arrays, you can bind, with an array, you can bind kind of like it's like a little a dot syntax to kind of bind, like, ignore more than one thing in an array. So you can get just the head or the tail of a thing. Also structs too. So you can bind just like a single field of a struct pattern matching wise. So
yeah, and
cool.
I think the way that I think of this feature is that it lets you destructure without while reusing existing variables. That's like the key part here, right? That you don't have to sort of generate new variables, for the lack of a better terminology here. You don't have to declare new variables in order to destructure. You can use the variables that you already had.
Yeah, and more than just being nice, it's also sometimes really important for, like, if you're inside like a nested context where, like, the variable is declared in a higher up scope, then kind of like, if you want it to exist outside of the scope, well, you can't declare it inside the scope there. So you have to, like, originally you would have to like bind it to a new thing and then rebind it to the mutable thing that's in the higher scope. Now you just don't have to do that anymore.
Yeah, exactly.
So a pretty cool feature, I'd say.
This next one is arguably, like, it is a major feature, but it's also mostly feels like an ergonomics improvement. So this is around const generics, where now not only can you declare default values for const generics. So if you have, like the example they use in the release notes is you have an array storage struct that's generic over t, which is the element type, and const n of usize, that is, the number of things to store in the array. And now you can say const n colon usize equals 2 to say that if the user doesn't specify what n is, then assume that n is 2. This is the same thing you could do with type parameters. So this just feels like now const generics aren't special in this way. They do what the rest of the language can do. And the same thing now applies to allowing const generic type parameter or const generic parameters to be interleaved with generic type parameters. So in the sort of minimal implementation of const generics that got stabilized a little while ago, all of the const generics had to be at the end of the parameter list. So you could have a function or a type that's generic over, t and u and const n and const m. But you couldn't say t n u m. You had to have the const generics at the end. Whereas now you can intermix them. You could say t n u m and it's fine. And again, like, it was pretty tricky to get that to actually work internally in the compiler, but for as a user, it just means that const generics works more like type generics now. And it's more that you're not going to run into as many limitations of it that you otherwise would. So it feels very much like just an ergonomics improvements, or a lack of surprising behavior, perhaps. That's not to diminish the value of this feature, but it's just like it feels like completing out the feature that we already had, which is really nice. And then we have our good friend, future incompatibility warnings. We've been around the block with this a couple of times, trying to distill down exactly what it is and what it's for and why it's useful. And I think in the 159 release notes is a pretty good explanation of exactly what's going on here. Do you want to tackle it again, Ben?
Yeah, sure. So, if if you've ever built like a Rust project with like kind of long lived with plenty of dependencies, you've probably benefited from, but maybe didn't appreciate the fact that whenever you compile dependencies, it doesn't spit out warnings at you for your dependency you're compiling, right? Or at least it doesn't ever like even. We put it this way. So in Rust, it is possible to use an attribute called deny warning. So any warning you see, anytime you ever see like a warning for must use, like you were saying before, you can in your own crate elevate that to an error. So you can say, hey, when you compile this code, please error out whenever this happens. The problem is that Rust wants to introduce new warnings from time to time, and one of the things that you can do is just like deny all warnings as errors. And so this is actually one of the reasons why. So like in like GCC, right, adding new warnings is kind of a big deal. And so in GCC there's like there's -w, there's -w all and -w everything, and kind of like because they don't want to break workflows that expect a set of warnings to never change. And so in Rust, it will kind of just suppress warnings in dependencies as a way of kind of like saying, hey, we might introduce a new warning here, but we don't want any of our existing users to break just because of a warning, right? Because people tend to expect warnings not to break their code. The thing is, though, that warnings are also used for like more than just like nagging you about like must use things, right? They're also used for a new purpose, which is not saying new, but one of the distinct purposes is that when Rust wants to deprecate something that's really important, because normally Rust would kind of like bend over backwards to try and find a way not to remove a thing that didn't need to be removed. Although sometimes there are like things that are clearly broken, right? If there's like a type system unsoundness, say, that might involve a compiler upgrade that makes a thing that compiled previously no longer compile, and it's probably the case that the thing that was compiling was wrong and potentially unsafe in certain contexts,
Dangerous,
but
maybe even.
it's still dangerous. But it needs to be fixed, and so it's kind of unavoidable that it will brick your code. But they want to give you a heads up beforehand, is the thing. So before they remove that feature, they want to make sure that everybody can see that all of the warning, see the warning that's occurring. So it's called a future incompatibility warning. The problem is that because Cargo is squelching all of the warnings, that if you're compiling a big long dependency list and one of these future incompatibility warnings happens, then you aren't seeing it. So like you might not notice that, hey, like if you upgrade your compiler to this thing that removes a thing, it might break. And so in practice, this means that almost all future incompatibility warnings have never been promoted to errors. The Rust compiler has lots of these warnings. And so like the fact that they're warnings means that like, people who compile their crates will see them and say, oh, this is probably a problem. I'll like upgrade this. But the Rust team has been very reluctant to ever actually promote any of these warnings to actual errors and thereby like remove all the bad code and all the compatibility hacks that are needed for this, even across editions too. And so this feature is really important because it means that future versions and editions of Rust might actually have the gumption to start removing some of these like obviously broken things that exist only for compatibility and that shouldn't, exist in any kind of ideal version of Rust. So I think the next Rust edition is going to be interesting because it'll probably, I assume, I'm not the Rust dictator, but I assume that there will be many warnings elevated to errors in the next edition that are of this nature.
Yeah, and I think it's a great way, as you say, to sort of unblock work on fixing things that might break some users, but giving people enough warning ahead of time and making sure that they will actually see those warnings. If they are attentive to their projects, even if their dependencies are not attentive to new warnings. There's also the associated cargo report command that gives you like a full report of the code that will be rejected as well, which is a really nice way to get a sort of complete picture of all of the potential issues you might run into the future. And the hope, of course, then is that when a user discovers that one of their dependencies has this problem, you can go back and tell the authors of the dependency, hey, look, you now have a new warning, even though you weren't actively looking for this. Here's a fix for it, or at least now you are aware, and hopefully we can drive the ecosystem forward in that way. There's another neat addition in 159 that hits probably a small number of people, but it's going to make them very happy, which is the ability to create stripped binaries. So in general, Rust tends to develop or build binaries that include debug info. And in particular, it includes debug info from things like the standard library. It includes debug info from your own code. There are ways to turn it off, of course, and it's been possible to strip that out after the fact manually. Like you can use the strip command, for example. But now Cargo and Rust C supports stripping out this debug info when the binary is linked. And you might wonder, why do you want to do this? Well, the primary driver for this tends to be file size. Usually when you end up with very large binaries, it's really just because they have a lot of debug info in them, and stripping them can often make them significantly larger. Like we're talking order of magnitude here. And so if you have a binary that you're deploying somewhere where you don't need like symbols in backtraces and you're not going to run GDB on this particular binary, it might make sense for you to strip out the debug info. And so now you can set the strip option in your cargo.toml for a given profile. You can set it to debug info to remove the debug info. So this is stuff like the source file and the line number that is associated with any given line of instructions. It also includes things like caller, some information about the caller graph. You can also be even more aggressive and set strip equals symbols, and that removes all of the function names as well, which can also add a bunch of bloat to a binary or a shared library file. Of course, if you do that, then if your program does crash, all you're going to get back is like a list of addresses and no names, which might be too far on the side of this gives me nothing useful. But if you're working in, say, an embedded context, or you're working in a context where you know that the output from a crash will never be useful anyway, like for example, it always gets dropped, then this might be a good way to optimize your binaries like that. I think that leaves us with the last sort of big ticket item for 159, which is incremental compilation being disabled again. Do you want to talk a little bit about this, Ben?
Yeah, sure. So last year, people will remember that and there's like 152 or something. There was a release where incremental compilation was disabled, and what incremental compilation is after you compile your Rust code, it remembers parts of the compilation and then will reuse bits that haven't changed. And this is important because in Rust, unlike say in C or C++, the compilation unit is pretty big. It's not just one file; it's the entire crate. And so uh, naive model of compiling Rust is you take the entire crate at once. You like get the entire abstract syntax tree of like every single thing in the crate, and then you compile all of that at the same time. Better, if you only change like a single line of code somewhere, better would be just to figure out which branch of the syntax tree you changed, and then like reuse every single other bit that you've already compiled, and just like recompile the one part you need, and kind of neatly plug in what you've changed to the original artifact, and just use that from there. So right now, it's also, but the thing is, it's a very complex and wide-ranging feature. It's I was observing some of the discussion from the compiler team in the wake of this change because it came very late in the release cycle. I think a few users, like a few days before the release, reported some bugs, and it was just like fixing them caused even more bugs. So they didn't want to backport the thing necessarily without a risk of like causing like a cascade of like ever larger bugs. And by bugs, I mean compiler crashes. These didn't appear to be miscompilation. These were actually silly. It's still bad, but not quite as bad. A compiler crash is called an ICE, an internal compiler error. And it just means that like, oops, Rust crashed. But yeah, it's better than giving you wrong code by default, right? And this was actually what happened last year, was increasing these checks to make it crash more often and reduce the risk of miscompilations happening silently. So in this case, it's a bit frustrating, certainly, because the fix is already in 1.60. So if you want to not suffer the loss of by default incremental compilation, you can just use beta. So like rust up toolchain, install beta, rust up default beta, and now you're using beta, and that would actually help a lot, because one of the reasons that this slipped through is that not a lot of folks actually use beta for regular development. Plenty of folks use beta for CI, which is a nice service that they do for us. I say it for us, for the Rust ecosystem in general, because it reveals any problems in beta before they get to stable. But CI doesn't check specifically incremental compilation, because every CI always builds from scratch, right?
Yeah, I would even go as far as to say that I think most people should be using beta for their day-to-day development. Like,
if you're so tech savvy that you're listening to this podcast, you're a pretty cool person, and you should use beta. You should upgrade to Rust beta.
yeah, rust up default beta right now.
Live on the not so bleeding edge. Live on the, I guess, like, what's like between bleeding and not bleeding?
Lightly wounded?
Live on the lightly wounded edge.
Bruised.
Live on the bruised edge.
Yeah,
there
right.
you go. Live on the bruised edge and use beta. Use it today. It's essentially as stable as stable. It has like maybe like one change in a week, one commit per week, backported from nightly on average.
Yeah, and
So,
you're helping the Rust project. You can report issues because you do report issues when you find them, right?
mm-hmm.
Just checking with our audience here that they know that if the compiler crashes, they should file a bug. But otherwise, like, there's no reason really not to use beta. Like, the only downsides I can think of are you may run into an issue. It should be rare, but if you do, that's super valuable information to report back. And the second reason might be you might accidentally make your code rely on a feature that is in beta but not in stable, but that should be pretty quickly caught once you try to push this in a PR and the stable build fails.
Yeah, to clarify, feature flags don't work on beta. So beta is the same stability guarantees, or the same stability API surface as stable, the stable branch. It's just that.
Yeah, so this would just be like something that has been stabilized but hasn't landed on stable yet because there hasn't been a stable release since when it was stabilized. So it should be a very small set.
Mm-hmm. Yes.
And speaking of stabilizations, I think we can get to the stabilized APIs for 159 now. There aren't any ones that I think are very important to call out, except maybe the available parallelism function.
Yeah, that's a cool one.
This is one that I've wanted for a while. It comes with a bunch of caveats. Like I recommend reading the limitations section of the API, but very basically, it tells you how many parallel tasks, how much parallelism your program is probably able to get out of whatever host it's running on. So you might think of this as sort of like your core count, right? Like if you're on a 16 core box, available parallelism will probably give you back the number 16 and tell you that's how many threads you should run in parallel for something like Rayon, for example. Um, and it's something where we've already had crates like num CPUs that people use for this kind of functionality, but at least now we have it in the standard library, and you don't have to reach for that. Um, One of the caveats here is that it is a very lightweight mechanism, which means that it doesn't consider a lot of potential other factors that impact your available parallelism. So this could be things like, if you have multiple different NUMA regions for like very large core count boxes, then that's tricky. It doesn't take into account if you have processors or co-processors that have different capabilities. It just gives you a count. It doesn't do things like measure if the OS has like soft disabled a core for your process. So there are some complications here if you really need an accurate count. But in general, this is going to be a good place to get a sort of rough estimate of the parallelism of the computer from.
Yeah, and this ties back into as well the kind of what I was talking about earlier with regard to trying to avoid like micro dependencies, where I think there's a crate called num CPUs which just like provides this. And the thing
Yeah.
is, this is kind of a building block that's kind of required for doing any sort of like at scale parallel computation. Where like, okay, like I don't know what how like many like threads or cores my current machine has. Please tell me. And Russ is like, please get a crate for that. Which isn't the worst thing, but like if it's possible to kind of grab take this like micro thing and move it into std, if it's like a very fundamental building block, that's just like a pure win in my mind.
Yeah, and I mean the num CPUs crate I think is probably still useful because it does implement some of those more that more like sophisticated complex logic for determining the amount of available parallelism that you could sort of, if all you need is just basically the core count, then use the one from the standard library. But if you really need to like explore the processor tree and make sure you only look at processors that aren't masked by the OS and stuff, then I think bringing in something like num CPUs is totally reasonable. But at least now you have for the simple cases something to reach from that's provided by the standard library. Um, uh, I don't think the other stabilizations are that interesting to get into. But I did have some things from the changelog. Um, Unless there was one of those any of the stabilizations you wanted to highlight.
Well, I mean, there was the ARM v8 neon intrinsics for ARch64. I think
Oh
you were
yeah,
kind of like saying, I have no idea what this is, but I think there are some folks I saw on the Reddit thread. There are plenty of folks. This is SIMD for ARch64. So I mean, like SIMD is still coming along, but it's just an enormous task that it happens very slowly in fits and starts.
yeah, that's true. Yeah, and I guess it is ARM v8 is like the sort of next gen or last newest gen, I guess, of ARM processors, if I remember correctly. So it is exciting that we're sort of continuing to improve on the ARM side of things too. I just want to know when I can get an ARM laptop running Linux that has decent specs.
Mm-hmm.
But that's neither here nor there. For the changelog, one thing that I thought was nice was Cargo now has support for the -r flag, which is exactly the same as --release, but it is shorter. So now you can do cargo run -r. And in fact, if you didn't know this already, Cargo already has shortcuts for the aliases. So instead of typing cargo test, you can type cargo t, and it does the same thing. And now you can type cargo t -r to run all your tests in release mode. Or similarly, cargo run -r. I think you could do cargo r -r, which is its own kind of funny. But it's just like a nice, now you can type less when you run things from the command line.
And you can like have your shell alias cargo to C, so you can do C space R space dash R. And you can
Nice.
put all these in shell scripts, and someone will have to maintain them forever.
It's the new R only language where
Yep.
all of your commands are R's and spaces and minus. R, R, minus R, 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 minus R.
Pirate Lang.
Yeah, it's R. The other thing that has stabilized, and this is not going to hit you immediately, but it is like a longer term effort that is cool to see come to fruition, and that is the symbol mangling version argument to Rust C, which is now stabilized, and it's stabilized specifically in that now you can pass dash capital C, so a cogen argument to Rust C, symbol dash mangling dash version equals V0. You cannot set it to any other value, and V0 is not the default. But the basic idea here is that the Rust compiler has implemented a symbol mangling scheme that is better, that more accurately represents Rust codes when expressed in debug symbols than what's being used currently. And that's called the V0 version, because the legacy version is just sort of a hacked together thing that we use, but doesn't really have a stable name or any kind of principled approach to it. So V0 is really the first thing that's stabilized. And the symbol mangling is basically the way that Rust takes a given function name or type name in Rust and turns it into like ASCII that can be put into the debug info tables in your binary that can then be displayed by things like GDB. And there's been a lot of work to try to get out this new, better symbol mangling algorithm, because it also meant contributing to all of these upstream tools that read debug info so that they understand this new mangling syntax. But that work has gone really far along, and there's been a lot of work to like upstream this into GDB and LLVM and perf and valgrind and all of those various tools. And that's now finally getting towards the end here, and they're happy enough with the symbol mangling scheme that they're now ready to make it stable. It is not the default yet. That PR is still open and sort of pending some upstream patches, but it is an exciting forward progress.
Yeah, this is a great one of those things where it's just a language maturity thing. Where so the existing symbol mangling scheme exists like purely for like convenience, because like you need to mangle symbols somehow. Because unlike in C, where you just like symbols are named what they're named, if you have generics, then you can have many things named the same thing if you're not careful. And so you need to have like some way of making them all unique, so that like when you actually go to call the symbol, you know what you're calling. And so the current and legacy version is just to like hash some like completely arbitrary compiler internal like details, and then like append those to the name. And so that's like one kind of like terribly hacky, then like no other compiler other than Rust C would ever like, you know, be able to reproduce that. And two, you can't reverse that. So if you are like a GDB, you can't look at this hash and say like what like originally was like all of these arguments. So like what were the type parameters to this thing? Like what was the path of this thing? And so the V0 RFC for the Mega, I'm not sure what's called V0. You could just call it V1. Honestly, it's kind of weird.
I mean, yeah,
no one would have stopped you. But the RFC is an interesting read where like if you want to see like, you know, it's based on the C++, I believe the Itanium ABI for mangling. So there's plenty of prior work. There's like built-in compression of symbols to like help avoid like giant exploding long symbol names. So it's also it ends up being more precise than the current mangling, easier for tools to consume, more consistent, actually specified. So other implementations of Rust could actually do it. So yeah, it's pretty cool, and it's been a big effort. It has to coordinate with like lots of external upstream tools. So I commend everyone who's working on this. It's been a long time coming.
I think the last thing I wanted to highlight, and this is maybe arguably stupid, but the hash map and set methods into keys and into values were moved from one impl block to a different one in the standard library. And specifically, and retain, I think. They were moved from an impl block that had the requirement that the key type implemented econ hash to an impl block that didn't have that bound. And the observation here is like, if you have a hash map and you just need to grab all the keys or grab all the values, it's okay for the key type to not implement econ hash because you're never comparing keys. And it's a change that probably doesn't matter to anyone, because normally when you create a hash map, like, you're going to be looking things up or inserting things, in which case you need like the key types to have econ hash. But it is a nice way to specify the sort of minimal requirements of each methods. And the reason why them being minimal matters is every now and again, you actually do need to construct a hash map with a key type that is an econ hash, because all you're doing is like, creating it and then dropping it for some stupid reason. Like you're writing a macro and the macro needs to generate code in this particular way. And so you want it to work even if the type doesn't meet the bounds, because you know that you will never insert anything. This should be extremely rare, but it's one of those that's just tidy up the bounds of each function so that they're actually the minimal stuff that function requires. So I thought it was just nice to see that a PR landed that really just did something that basically doesn't matter to anyone, but is just, it sort of appeals to the OCD in me of, it should be right, damn it.
Well, I'd say this is it's kind of an opportunity for intermediate level Rust learning, where if you actually go into the standard library and go to the hash map docs, you'll see that you've heard of inherent impls, where you just have so you say impl foo and then a block, and you can put various methods on there, no trait involved. Maybe you haven't realized that you can have multiple of these, and that all of these can have different generic bounds. And so this is what hashmap uses. And so if you go to the fn new, you've seen the new method on hash maps, hashmap : new. There's actually no bounds at all on those generics, and so you can make a hash map with any types at all. Now the thing is, as we're mentioning, the insert methods are all in a different block, which have different bounds. So it's kind of a neat API design where it's like, yes, this is fine. Rust allows this. There's no problems here. And it precisely identifies what methods are available at which times. So it's pretty cool, because it's kind of it makes you realize that methods aren't inherent to the types themselves. They're based on what types you want to use them with is when they exist. They don't they're not always there. The actual types that you bring to the table, it determine which types which methods even exist in the first place. So I don't know. For me, it was a pretty big revelation.
Yeah, and you can see this when you look at the Rustdoc output, right? It shows you which impl block each method existed in, and it shows you the bounds for that impl block. And there are libraries that use this to their advantage. For example, I maintain a library that does it implements sort of like Selenium, like browser automation in Rust. And there I have an impl block for each category of operation you might want to do with the browser. They all have the same bounds, but it's a nice way to group together functions that do similar things. And you can even write documentation for a given impl block to say, this impl block is about this kind of stuff. And it's just a nice way in which you can be even more organized and principled about your documentation and your API design. I think that leaves us at the end of 159.
Yeah, I believe that's it.
I would like to thank you, Ben, for bringing us all the way to 159. I think we're in a position now where we have to wait until 160 to talk again. That is the policy that we've instituted.
No, 161 even.
Oh, you're right. It's going to be 12 weeks, Ben. How am I going to survive?
How will I live without you? Can we get copyright struck if we're not in YouTube? I have no idea.
I mean,
they'll find a way.
Someone
Google
will probably sue us. Although that said, given all the shit we talk about Rust, I'm amazed that the Rust team hasn't sued us yet.
They're working on it.
Yeah, I think the core team is probably coming after us anytime now.
All right, well, we should get a move on then before they find us, our locations.
Yeah, I'll go hide.
They're tracing the call as we speak.
That's right.
I'll see you in 12 weeks.
All right, bye, everyone.
Bye.